Okay, let's get started. Here we go. Here we go. Okay, can you please stop talking now? Here we go. So we got this monk so against the wall right now there's a ladder. And so there's this very tricky monkey, and he's going to kick the ladder, and it's going to set the ladder falling. And this will show it again and again, over and over again. So that ladder is 10 feet long, and he gives it a kick, and starts flat against the wall, and then it falls, as you see. And so the question is, how fast is y, the distance from the floor to the top of the ladder, changing with respect to x, the distance from the wall to the bottom of the ladder? So let's just pause it here, just any typical situation here on the way down. Okay, that's good. So what is it asking for? So here's what we got. X is the distance from the wall to the bottom of the ladder. Y is the distance from the floor up to the top of the ladder. Okay, are we ready to start? And then the ladder is 10 feet. So when it asks for this here, how fast is y changing with respect to x, how can we represent that quantity? What's being asked for? How can we represent it? What's the question that's being asked for in this problem? How can we represent that symbolically? We all should know that. How fast y is changing with respect to x changing. Okay, someone said dy dx, y prime. Okay, these are both ways that we could talk about the rate of change of y with respect to x. That's what's being asked for here. And so based on your homework that you did, what do you need first to determine y prime? So if we want to figure out what y prime is, what do we have to have first? What's that? Accumulation function? Okay, but so in your homework though, we really didn't have accumulation functions anymore. We had something else, right? Something a little different than that. What did we have? An equation. An equation of x and y, right? So you start with an equation of x and y, and from that, we could get this rate of change of y with respect to x. And so, what is the equation of x and y? Yeah, right. Kind of gave it away there. So let's look at the picture again. So we need an equation of x and y in order to get y prime or dy dx. And so here's our relationship. X is this horizontal distance, y vertical distance, and the ladder is 10. So what could we use to get a relationship of x and y that stays the same as this ladder falls? Yeah?
Y squared plus x squared is equal to 10 squared.
And how do you know that?
A squared plus b squared equals c squared.
Right, and so is that true no matter where the ladder is?
Yes.
So like for this here, if that's still true, x squared plus y squared equals 10 squared here? And then if the ladder slides a little bit further, so what I'm asking is it always true as this ladder is moving? Is x squared plus y squared always equal to 10? Yeah, you get different triangle, but it's still this right triangle, so that x is the base, y is the height, and that hypotenuse is 10. So x squared plus y squared equals 10 squared. And how are we going to find now this rate of change dy dx? How are we going to find this rate of change dy dx? Okay, so this is what we did Monday and what's in your homework. First step is to think about taking the rate of change of both sides This should all be familiar. We got the rate of change of a sum on the left, the rate of change of a constant on the right. So we get x squared prime plus y squared prime equals 0. X squared prime is 2x. Y squared prime is 2y. Y prime equals 0. Solving for y prime, we get minus 2x over 2y or negative x over y. And so we could also write that that's dy dx. Okay, so this equation then tells us what the rate of change of y is with respect to x for any position of the ladder that it's in on its way down. Okay, so how fast is the top of the ladder falling when the top of the ladder is 8 feet above the ground and 3.5 feet above the ground? So take a minute or two and see if you can figure this out. Okay, so how fast is the top of the ladder falling with respect to x? Okay, when it's 8 feet above the ground and 3.5 feet above the ground. See what you can do on this. Go. Yeah. Okay, right here, this gentleman here, black shirt. Tell me how you did it.
I really couldn't figure it out, but first I was trying to figure out, well, 8 feet and 2.5 feet was x.
So 8 feet is what? What is 8 feet?
Beginning where like x starts.
That's x. X equals 8.
So y.
You tell me, which is it?
Y.
Okay, y equals 8. And so what are we going to do with that?
Plug it in for y.
Plug it in for y. Into what?
Y squared.
So what's the goal? What are we trying to do?
Well, after we do that, what happens next?
Okay. So you're going to plug 8 into this to solve for x? Is that what you're saying?
Plug 8 into y and solve for x.
But I've got two different things here. So do you want to plug it into this red equation or this down here?
Plug it into x squared plus y squared.
Okay. So he wants to plug it in here.
So 8 squared.
And what do we get for x for that?
6.
6. So what does that tell us? When the height of the ladder is 8 feet, then the bottom is 6 feet up from the wall. So I'm going to take it over from there. Let's see. How about right here in the white shirt? Where do we go from here? Yeah? Yes, you. No. I love New York.
Oh.
Plug it into the dy dx.
Okay, so what are we going to get? So dy dx equals?
-6 over 8.
And I think that's negative 0.75. What is the units on that? What's the units on that number?
Feet per feet. Vertical feet per.
Vertical feet per horizontal feet. So feet per feet. What does it mean? Negative 0.75. Yes, sir.
Does it mean that for every foot x moves to the right,
Okay.
y is coming down 0.75 feet?
Okay, he said for every foot that x is moving to the right, the top of the ladder comes down 0.75 feet. What do we think? What's that? With a small change in x. What were we going to say?
I was going to say when x is or when y is equal to 8 at that rate, so it has to be at that specific.
Okay, so in this particular scenario, when y is 8, for a small change in x, is y going to come down more or less than that change in x? Less, about 3/4 as much, right? So for a small change in x, we're going to see that the ladder drop about 3/4 of whatever change in x we have. But that change in x has to be small, because if the change in x is too big, what happens? The rate changes, right? The rate's going to change because the ladder's going to be in a different place and we may have a different rate. So that's why we're saying for very, very extremely small change in x, we get a change in y that's 3/4. It decreases 3/4 as much. Okay, so we got x and y and dy dx. So let's make a little table here. So we wanted the rate of change, but we were only given y, right? And so how is it that we could get x? Well, we have this relationship that's always true about x and y. So we get we get x first, which is 6, and now we can set up dy dx. So when x was 6, y was 8, dy dx, negative 0.75. Next, and I said 3.5 feet above the ground. So which of these is 3.5? In order to get dy dx, we need to get what first? So we need to get x first, and someone got that? I heard this. Someone else? Does that agree? So, cool. Okay. And what do you get for the rate of change? Negative. I'm hearing negative 2.6. So, tell the person next to you, what does that number mean? Negative 2.68. What is that number telling us about the situation? Go. Okay, right here in the white shirt, young lady. Yes. What did you guys talk about? What's the negative 2.68 mean?
The rate at which is changing when it's 3.5 feet above the ground.
Okay, so at 3.5 feet up, so maybe can I try to get that? Okay, so that's pretty close. So at 3.5 feet up, you're saying it's the rate at which it's changing. Well, what does that mean, though? The rate at which it's changing. Can you make some further conclusion about that?
For every change, unit of change, that's the amount times that.
Okay, for every unit of change of what? Of y? Of x. So for every unit change of x, this number is? What's that?
It's changing at a rate of
Changing at a rate of negative 2.68. What does that mean? It's changing at a rate of negative 2.68. Yeah?
For a small increment in x, y is changing negative 2.68 times that. And 9.27.
Right. If we took a small change in x, we'd expect y to go almost 3 times down as far as that whatever change in x we pick. But that only works for a very small change in x, right? It only works for a very small change in x. Okay? It's getting faster. Let's see. She's saying, is it getting faster? Yes or no? All right, let's watch it. So watch the top of the ladder. So, is the top of the ladder getting faster? That is true. Is the rate of change increasing or decreasing? Is the rate of change increasing or decreasing? Have it out with the person next to you. 30 seconds, go. Okay, how many people say increasing? The rate is increasing. How many people say the rate is decreasing? It's either one or the other. Okay, the rate of change is these values are becoming more negative, right? Becoming more negative. Okay, so what kind of, if a sequence of numbers is becoming more negative, are those increasing or decreasing numbers? Decreasing. This rate of change is decreasing because the rates are getting more negative. Yes, it's getting faster, but if we're talking about increasing or decreasing, that has to do with whether the rate itself is positive or negative plays into that. Yes, sir?
I think it would help to remind yourself the difference between speed and velocity.
Right.
Speed is always positive.
Right.
It's the absolute value of velocity.
Right.
Velocity has
So when we're talking about it's getting faster, that's just talking about speed. Relative of, doesn't matter, direction doesn't matter. Okay? Velocity then brings in positive or negative. So these values are decreasing. Yeah?
So can we say it's decreasing faster?
No, so that would be a matter of the rate of change of the rate of change. So don't say that. Yeah, so that you're making it more complicated. The value of y, the rate of change is decreasing. The value of y is changing faster. You could say that. That's the value of y, though. But then the rate of change is decreasing. Yeah.
Could you say it's decreasing at an increasing rate?
That's still a great rate.
Yeah, but you're talking about the rate of change of the rate. We're not talking about that. You're talking about the rate of change of the rate. Okay? So, when you talk about the rate of change, this rate of change is decreasing because the rate of change is getting more negative. And that's negative. But this is very difficult because you really want to think, you see that thing getting faster, you see this number, the magnitude of this number is bigger, so you want to think that this is increasing. But it's not. But we'll practice that over the next week or two with other examples, but that's just a foreshadow. When numbers get more negative, they are a decreasing sequence of numbers. Okay, so here's a recap of the math we did. We started with this equation, and we found the rate of change of y with respect to x. And we said that that's how fast the top falls relative to the bottom, moving in feet per feet. But now a new question. How fast is the top of the ladder falling in feet per second? How fast is the top of the ladder falling in feet per second? So now we're introducing something new. What are we bringing new into this that we didn't have before? Time. Okay? So we have the third quantity, time, and to be specific, we want to be specific about our quantities. The time in seconds since the monkey kicked the ladder. So now we have 3 things going on. We have the horizontal distance from the wall to the bottom of the ladder, the vertical distance from the floor to the top of the ladder, and the time in seconds since the monkey kicked the ladder. So if we want to talk about how fast that top of the ladder is falling in feet per second, we need to know something about now how x is changing with time. So suppose the bottom slides out at a constant speed of v feet per second, okay? And so if you want to make that 2 feet per second or something like that, but v could be any constant speed. So if that's the constant speed, then how would we write and say, this is our variable t, say down here. If this is t, then what would x equal? What would x equal as a function of t if the bottom slides out at a constant speed of v feet per second? Could you find what x equals? So after 0 seconds, how far is the ladder gone? After 1 second, at v feet per second. After 1 second, how far is the ladder gone? V. After 5 seconds, at v feet per second, 5 v, right? No, 5t. These are t's, sorry. I don't know what I'm doing here. So what am I trying to do here? T and x. All right, so I'm a little confused, but anyway, this is what I mean. I don't really think that table through anyway. So for every second that goes by, you're going to go that many v's. If you're going v feet per second, then for that many seconds, you're going to go that many v's of feet. Okay? I was right. I was just confused. Okay. So this means that our rate of change of x with respect to t is v. Just right? If it's vt and you take the rate of change, then your rate of change will be v. But that's what I told you in the first place. I said that the rate of change of x was constant at v. Okay, so these two statements should make sense. Okay, so now we still have this relationship that's true no matter what the time is. We still have this triangle that makes the Pythagorean theorem true. And when we take the derivative now, we're going to take it with respect to t, because what we want is dy dt, not dy dx anymore. Right? If we want how fast the ladder is falling in feet per second, then we want dy dt. But then what does that mean when we take the derivative of x squared? X is now, look, x is a function of t, just like y is a function of t. So it's going to require the chain rule as well. Okay? So we have 2x, but we're taking the derivative with respect to t instead of with respect to x. So now we're going to have 2x dx dt by the chain rule, and 2y dy dt by the chain rule. Okay? Because we're not taking the derivative with respect to x anymore, we're taking it with respect to t. Does that step make sense? So if you're doing this with respect to t, then every term is going to have chain rule on it. Okay? Instead of just the ones that had y. So we can change that around, and you get dy dt equals negative x over y, but now times dx dt. And we know that dx dt was given as v. Okay? But this is what's called a related rates equation, because this is the first time we've seen in this course an equation that has two rates of change in it. Okay? So this is how the speed of the top of the ladder relates to the speed of the bottom of the ladder with respect to time. Okay? Or actually, the velocity. Okay? So the velocity of the top of the ladder, how it relates to the velocity of the bottom of the ladder. So what was the source? This is kind of the big theme for today. Where's the source of the related rates equation? Because related rates is that's our topic for today. Equations that bring together two or more rates of change. Where did it come from? How are we able to get a related rates equation? Where did it come from? No, it's stuff we already did, right? Where did it come from? Where did it come from? Well, it came from the equation that related those quantities, right? So we have the rate of y and the rate of x together in the same equation. In order to get that, we're going to need an equation that brings together x and y. This is going to be the key to solving these problems. And then we use implicit differentiation to derive the related rates equation from the equation of the quantities. Okay, so here to emphasize. To get the related rates equation, you first must have the equation that relates the quantities for those rates. Star, check, highlight, okay? This is going to be the key to solving these problems, that you have this general strategy in mind. Anybody have a question? Okay, so let's do an example. So the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So it mentions two rates, right? It mentions two rates. What are the two rates that it mentions? What's the first rate that it mentions? How the edges of the cube are changing, and what's the other rate of change that it gives you? Or that it mentions? How fast the volume is changing. Okay, so we have these two different rates that it's mentioning. And so in order to get an equation that relates those two rates, how the edge side is changing, how the volume is changing, we're going to need what first? An equation of those quantities, okay? So we want an equation of the associated quantities, and from that we'll get the related rates equation. So we did this already. What are the specific rates involved? We said how fast the edge length is changing and how fast the volume is changing. So we know that we're going to want to get the quantities equation. So before we get the quantities equation, let's figure out then from those rates, what are the quantities that we're interested in? What are the quantities? This is the easiest step. Volume and edge length. All right, so we want to identify the quantities associated and assign variables to those. So edge length S, volume, I should say volume of the cube, be specific. Volume of the cube, V, and we know time and T. Time is, we'll use T. Okay, so now we're ready to write this quantities equation. We've got edge length of a cube and volume of a cube. So somehow, some way, we're going to have to figure out what equation relates those quantities. So what is it? Edge length of a cube and volume of a cube. So it's a pretty basic geometry formula that we hopefully remember. Yeah. So this is a function, volume as a function of side length equals side length cubed. And there's our quantities equation, right? So this was our goal to get started. We needed this quantities equation that related V and S, volume and side length. And now we're going to get the related rates equation by doing what? We're going to take, implicitly differentiate with respect to side length. No, so it's mentioning time here. So we have the edges increasing at a rate of 2 centimeters per second. How fast is the volume changing? Is implying that we want it per second. So this derivative is going to be with respect to time. Okay, so on the left we just have v. What's the derivative of v with respect to time? dv dt. And then what's the derivative of s cubed with respect to time? 3s squared times ds dt. Okay, so volume with respect to time is going to be dv dt. Side s cubed with respect to time is 3s squared ds dt. Or you could think of this as 1, right? 1 times dv dt. Because this is v equals s cubed. I just wrote it in function notation. Okay? So, but we're given ds dt, right? So it said ds dt, it says that the side length the edges of the cube are increasing at 2 centimeters per second. So we know this is 2. It was given. And we want to find, it says how fast is the volume changing, so this is our unknown. So all we have left is S. So what is that? What is S? That's our 50. So the edges of the cube are increasing at 2 centimeters per second. That's our ds dt. 50 is our current value of S. Okay, so this bar just means we're going to evaluate when this is true. So this vertical bar means evaluate this quantity when this thing is true. So that means that S is 50 squared, and we got 3, 50 squared times 2, 15,000 centimeters cubed per second. Okay, so this is a roadmap. These 4 bullet points are a roadmap that I highly recommend that you follow. But the main thing that's driving this roadmap is this right here. That you're going to write an equation that brings together the quantities that you want, the quantities associated with the rates that you want to relate. Any questions on this example? All right, well, let's see if we got it or not. You guys get some time to work on this one. See if you can do it. Okay. Okay, so here's the mindset. What's the mindset of this? We're going to have a related rates equation, so we need a quantities equation first that relates to quantities that you're going to want to relate associated rates for. Okay? So what's the strategy? Identify the rates involved. Identify the rates involved. Identify the quantities associated with those rates. Assign variables. Then you're ready to write the quantities equation that we're saying is the focus here. Quantities equation. From that, you can get the equation that relates to the rates. And then from there, we just need to solve for what the thing that we're trying to find. In this case, how fast is the radius increasing? Okay? So I'll give you some more time. But my question to you is, was this your approach? Was this your mindset? Okay? Yeah. Okay, related quantities. related rates. Related quantities, use implicit differentiation, get related rates. Once you have the related rates, then we can figure out whatever we need to figure out. What is it that they want? How fast is the radius increasing? What's the unknown then? What is it we're trying to find? This one now. So if we're going to find that, how fast the radius is increasing, that means somehow we're going to have to get every other value in that equation. So dv dt, do we know it or can we find it? That's 150. That's our given dv dt. Okay, if you're still talking about the problem, that's cool, just whisper. If you're talking about something else, so you're trapped. Okay. So 4/3 pi, whisper, times. So if we're solving for this, then that means that somehow we need to get the radius, or be given it. How can we get the radius? Because dr dt is our unknown? Yes, sir?
We know that the final volume of 500 just keeps
Okay. Whisper, please. Whisper, please. Whisper, please. Okay. Yep. So 500 is our volume, and we want the radius at that moment. So we can use our equation that relates the quantities to get r when v is 500. And that will be then what we need to finish solving for the rate of change of radius with respect to time. So a little bit of side work here. 500 equals 4/3 pi r cubed. And our whisper, please. And so if we want r, then when the volume is 500, it's going to be the cube root of all that stuff. And let's do we have a good approximation for that? 4.92? Is that what I heard? How fast is the radius of the balloon? So the sphere is filled. So the balloon is being filled. This is a great question, though. So the tank is expelling helium, but we're monitoring the radius and volume of the balloon. Are those increasing or decreasing? Okay.
It's increasing.
Yeah. So the tank, yes, it's leaving the tank, but we're talking about the sphere of the balloon, the radius and its volume, which are increasing, right? Increasing, so the rates would be, both of them are going to be positive, right? The radius is going to be getting larger and the volume is going to be getting larger. But that's a really good question because you have to read the information given. It may not be given negatives, but your rates may be negative because the quantity is decreasing. So you've got to watch out for that. Whenever a quantity is decreasing, its associated rate is negative. And that needs to be reflected when you plug numbers in. Okay. I just want to get confirmation that this is 4.92 inches. Cool. So this is our related rates equation at this particular moment, when the radius is 4.92 and the volume is 150. And so from that, we can solve for dr dt. And that's just taking 150 divided by all this stuff, right? 150 divided by this product. And someone have a good approximation for that? 0. And what are the units on that? dr dt. The units will be inches cubed per minute. What do we think? Yeah, the radius is in inches. So the rate of change will be in inches per minute. And what does it mean at that moment for a small change in time, small change in the number of minutes, the radius is going to increase half as much as whatever small change in minutes you had, right? About half as much, 0.49. Okay, questions on this example? Okay, so you will have more like this in web work, but they're all different. That's the thing. So all the situations, the contexts are all different. That's why I'm trying to really emphasize that you lock onto this idea that every problem, you're going to have you need to find that quantities equation so that you can find the related rates equation. That's really that should be your focus. So we got one top hat question.